Okay, thank you very much for coming, taking a seat. We don't mind. We haven't actually harmed any kind of animals during the preparations of this presentation. Evidence in the slides contrary. And I would like to present both of us. So I'm Barnhart-Magen.
I am Ezra, and as you all know, whenever somebody comes to DC or B sites and presents, I make them drink. So there is no event protection for me, so I will need to drink.
Smile.
So that was a selfie challenge.
Done. So I was here on this stage last year at OWASP 2017 to share some thoughts and some ideas about how someone would go about and attack AI systems. And I introduced a concept called adversarial machine learning with a couple of different perspectives on how you would actually look at what is happening in academia, in the world today, and how would that translate into actual attacks. That was 2017. Now it's 2018, and we're going to share with you the results of our last 6 to 8 months of research that my team and I have been doing at Intel on security for AI systems. We haven't done this work alone. We never do work alone. Nobody does. And we want to take this moment to acknowledge all of the different people and different research papers, presentation, talks that led us down this path and also helped us to build the research we're doing today. So you will be able to see at the bottom of the slide links and references to where we get the content and the data from. And we will be releasing these slides after the conference, so you don't really have to take a picture of each and every slide. So what are we going to talk about? We're going to talk about machine learning, what it is, what are the downfalls, where are the issues, and how would you construct attacks, and what exactly these attacks mean in the larger corporate business world scale on real-world production systems. Whenever you see something highlighted in yellow, this is something that I would like to emphasize and to help you to focus on what brings the most value from each slide. But we're not going to release 0 days. We're not going to describe how you would break specific systems. But we are going to explore and describe how you would break such system in general, some real-world use cases. I want to start with a story about a horse named Hans. Some of you may have heard me tell this story in different events. I will keep it very brief. Hans was a horse from 1903. It was very famous because it could do simple arithmetics. It could add simple numbers, 2 plus 3, 1 plus 4, 5 plus 1, stuff like that. And the way that he would do that, it was that someone would ask him a question, and then he would tap his hoof on the floor. Someone would ask 2 plus 3. He would tap his hoof 1, 2, 3, 4, 5. And then everybody would erupt in laughter and applause and everything because this was a very intelligent horse. But he didn't only do arithmetics. He could also spell in German, which is amazing for anybody, not just a horse. And a psychologist was contracted, and the task was trying to understand how come this horse was so intelligent compared to any other horse and at least some of the humans. And this psychologist came up with what we call today a double-blind test. And what he showed and what he researched and showed was that this was actually a very intelligent horse, but he couldn't do arithmetics or spelling. What he could do was read the body language of his handler. You can see in the picture here. In many senses, this is the same thing that happens with machine learning systems. So machine learning systems today are very, very good at solving well-defined specific problems. Whenever you try to give them any kind of generalized information, some other types of data, different domain knowledge data, they break, and they break horribly. And we're going to explore some of these paths today. So first of all, I want us to sit on like common ground. I'm not going to go very heavily into the math aspects of machine learning, or neither into the different algorithms employed in this area. If you have specific questions, I'd be happy to answer them later. But to have some common understanding, common language, when I'm saying machine learning, I mean that we have a system that takes many inputs into the system, usually input along with some metadata on that input. For example, it might be a picture here with a label. And that label might say, look, there's a flamingo in this picture. And I'll give it another input, and that label would say, there's a flamingo in this picture as well. And another input, now it will say a dog, a cat, a mouse, or whatever. So we are feeding lots of information into the system, and the system is built to discern and classify between the different inputs and try to extract the label according to what the metadata that we are feeding it. Deep learning is the same thing, but we're not providing any metadata. So the trade-off here is that if we don't want to provide metadata into the system, we have to provide a lot more inputs. And when I'm saying a lot more inputs, think of it about maybe 4 to 5 orders of magnitude. So you can train a machine learning sample with 1,000 samples. You want to train a deep learning system, you need 10 million samples, maybe more. So it works. Nobody really understands how, but it works. But you have to be very careful. When we're saying artificial intelligence, we mean something else completely. Because artificial intelligence is about context. It's about understanding. It's about reasoning. None of that is accomplished by machine learning or deep learning. When we're looking at this image, we look at it and we understand, OK, this is from a book. This girl is named Alice. She's going to use this flamingo in a moment as a croquet bat in order to hit that cute little hedgehog at the bottom. This kind of context is something that machine learning is not able to do. And no single machine learning algorithm can encompass and encode all of that information. However, everybody says AI. I also say AI, but what everybody actually means is ML, machine learning. So whenever you say AI, I actually mean ML, and I apologize in advance. So machine learning systems were designed to solve very specific problems, and they've been doing that for many, many years. Machine learning has been developed in the late 70s. It's not something new from last year. But the downside of them is that they are very, very compute intensive to build them, to train them, but also to get information out of them. But because they are designed to solve very specific problems, whenever you try to deviate from what they expect, you get funny results. Those funny results you would expect in a normal software system to be maybe you raise an exception or throw an error code or something like that. In machine learning system, you might actually get an output, which might be you will feed, you have a machine learning system that discerns between dogs and cats. You will feed it an image of a banana. It will say it's a dog. That's not a good validation strategy for a production system. You might feed it an MP3. It will say it's a cat. OK? So validation of these kinds of systems, especially in production, is a big major issue. I'm going to cover really very briefly what machine learning is composed of, but I'm not going to go into specific, the nitty-gritty details of each. So when I'm saying a machine learning model, what I mean here is the math behind it. How is the neural network constructed? What kind of parameters does it employ? The topology of the network, all kinds of that stuff is usually encoded in a configuration file, and you really don't have to care about it. The person who cares about that is the data scientist. Whoever is deploying those systems or trying to validate those systems in production doesn't care about what made the solution the solution. It just wants to make sure that the solution actually solves something. Okay? So we're not going to dive very deeply into how the solutions are constructed, but we're going to talk about what those solutions mean. And one of the major points that I want to emphasize here is that whenever people are saying, well, my company is doing AI or whatever, the model is actually the IP, is the intellectual property encoded by all of the research being done in that company. So if I can steal that IP, I stole the model, I stole the IP, I now have access to all of the deepest secret information that a company has. That's the trade secrets. That's the holy grail. That's the prize. Fundamentally, from a math perspective, most of the math algorithm thing going on in the background is multiplying pairs of matrices together. Different types, transfer functions, all that. But basically, we're multiplying matrices. Whenever we're multiplying matrices, we just get a matrix, a new matrix, or a new vector that represents the results of that matrix multiplication. A single-dimensional matrix is an array. It's just an array. A two-dimensional matrix is just an array. And just to make it simpler, this is what we're looking at. Whenever we're saying matrices, we don't really care about the matrix itself. We care about the representation of that matrix in memory. So whenever somebody is trying to scare you with machine learning, many multiplication of matrices together, blah, blah, math, blah, blah, ignore that. What we care about is that our buffers in memory holding the data that we want to protect or we want to steal. But in the end, it's just RAM. The machine learning process, especially in production, a lot of time looks magical because you put a couple of inputs up front, you get some outputs in the end. Just a question, if you recognize that reference, please raise your hand. No one? Really? Damn it. War games. Nobody watched war games? It's a tough crowd. OK. So we want to shed some light about what really happens between these different endpoints, between the interface where you upload or you enter your inputs into the system and the interface where you're actually extracting or receiving outputs from the system. So usually when people are talking about machine learning, they talk about the matrix multiplication part, but this is just one small nugget inside the entire workflow. So no matrix multiplication can actually work on an MP3 file or an image or anything else because it is expecting a matrix to multiply against. So there is an intermediate representation stage that somebody needs to translate from whatever your source input is, translate it into something that you can multiply with a matrix. So this intermediate representation, the encoding part, where you take your information and encode it in a way that the machine learning can input, is the pre-processing stage that is hugely important, usually overlooked, and there are lots and lots of vulnerabilities happening here, and we'll discuss this a bit later. Once we are done with the math part, and now we have some sort of output, we need to make sure that that output makes sense. So when we're looking at that output, we are getting a bunch of numbers. We are getting result 7 with result at index 7 with 0.78 probability of confidence. We get result in index 3 that is 0.05 confidence levels. It doesn't really mean much. So we have to create some human understandable information out of those mappings. So we have a mapping stage that takes those numerical responses that the matrix multiplication is giving us and translating them into something that humans can read. So we are attaching and mapping a string to each output from the system. So when I'm saying that I gave an input image of a cat to the system, and it says it was a cat, what I actually mean is that I took an image, I translated it into an IR, I did all of the math, I took the output, and I mapped the output into a string that says a cat. And now I know that this input is mapped to a cat, okay? So the training process, where most of the compute is invested in machine learning, is trying to get as many inputs as you can, label them correctly, and train the system to label new images such as that in the future, such inputs as that in the future. This is a very lengthy process, and this is what people are usually crying about when they're crying about machine learning. This takes a lot of time, a lot of compute, we need large GPUs, etc. We don't really care about that part. We care about this part. This part is usually called inference. Inference is the part of the system where you actually take your machine learning model, put an API on it, and connect it to the web. So this is the deployment. This is the production system that actually is making something usable out of this algorithmic nonsense at the top. The things that I want to cover, and a very strong message that I want to convey, is that machine learning models are not code. You can't read that code. It's not a code execution flow. It's just a matrix. There is no data structure that you can analyze in memory because all of those data structures are encoded into that machine learning intermediate representation. It doesn't look the same. It doesn't behave the same. And in the end, whenever you're looking at a machine learning model, you're looking at a binary dump of a matrix. You can't reverse engineer it in order to understand what kind of inputs caused this machine learning model to exist. So whenever we're looking at the binary, we want to reverse engineer it to understand the code flow and what kind of source code might have created that binary. We can't do the same thing for models. We can take a model and reverse engineer it to understand what kind of inputs created that model. And this is a big issue. It means that when we have a problem, when we have an issue with the system, it's very hard to debug it, almost impossible to debug it. Usually what most data scientists do when they have an error, they go back to the whiteboard and design it again. There's no tooling, there's no academic papers on how to do that. It's not doable today. Just to get a sense of what it looks like, hello, this is a machine learning model called ResNet, ResNet 50. You can actually see it in the header here. So this is just data. This is just a bunch of binary data that we can analyze and look at up to a point. So how would you actually go about and understand what a machine learning model does? What kind of validation techniques do you have? We are still struggling with doing validation for regular normal code. So doing validation for machine learning code is even harder. It's harder because there are different domains mixed here. Mathematical domains, data science domains, software development domains, production domains, DevOps, stuff like that. These groups are not very well mixed together. People who understand in data science have no idea what DevOps is. People who understand DevOps have no idea what kind of security implication specific models might incur in the system. So there's a large gaps in the knowledge of what could be done. But in the bottom line is, we're looking at code, but we don't really have code to look at. So what are we looking here? At what are we looking here exactly? And even if we are looking at it, at the right thing, and we have the domain expertise, it's just a matrix with values. We don't really know how to interpret it and how to make sure that it's the right thing, that it's behaving properly. And just to make this worse, when I'm saying model, it kind of sounded cute so far, but we're talking about binary files that are a couple of gigabytes in size. So a normal deep learning system might be around 10 gigabytes in memory. That's a large system to analyze. It's a big system to look at. Another thing that we should note is that machine learning models are based on the fact that you're giving them inputs that you're familiar with, that you've obtained, and you try to train them to predict the future. You predict the future based on events that happened in the past. So whenever you have something that is happening right now, and nobody's ever seen something like that before, you haven't trained the system to identify it. You have no inputs to identify it. It's a large gap to say that I have seen these kinds of events in the past, therefore I can predict new events that I've never seen before in the future. It usually just doesn't work that way. In the end, machine learning systems are designed to find specific signal points in the input, usually the strongest signal points in the input, and say, okay, whenever I see this kind of pattern, that means it's a cat. Whenever I see that kind of pattern, it means this is a virus. Okay, they're trying to home in and to lock onto what is the strongest signal in the input. And bias, which is what exactly am I focusing on? Am I focusing on the right thing? Is a big thing in machine learning systems. And here I'll tell you a short story. So there was a dermatologist who tried to train an AI system to detect tumors in skin conditions, cancer-related skin conditions, in order to make the research much faster and much better. And they did the research, they developed the inputs, they had all of the process in place, and in the end, they found out that they built a glorified system to detect rulers. And you can guess the reason why. So they built a very nice system that built on top of lots of images of tumors, but the strongest signal in these images wasn't a tumor, it was the ruler. So now they had a very strong system that whenever you put an image of a ruler into the system, it would say, yes, this is a cancer tumor. And the reason for that is that that's the way machine learning works. We push a lot of inputs inside, and if you're not very, very careful about what kind of inputs we introduce, we're going to introduce noise. And that noise might be stronger than the data that we're trying to enter into the system. So a lot of what we're doing, a lot of what data scientists are doing, is trying to filter out noise from the samples. We took a look at the most common attack vectors from our analysis and what kind of attack vectors could be done on these kind of machine learning systems. And we are using the common CBSS scoring that most of you are familiar with, and we came up with this mapping. So here you will see highlighted in red in the center the top 5 attack vectors that we're going to discuss today. In the gray ones are ones that we're not going to discuss today. So this is our scoring. So we took CBSS and we scored them accordingly to what are the most interesting ones from a CBSS severity point of view. So denial of service for machine learning systems is relatively easy. You will see a demo in a moment. Misprediction, which means I can choose my own inputs to create whatever outputs I want from the system. Pretty scary, not that hard. Model tampering, you will see a demo in a moment. IP theft, very, very interesting. I'll go into that in a moment. And backdoors. Backdoors is something unique that I will touch on in a moment, but backdoors in the machine learning world are much more interesting than backdoors in normal software, because in normal software, someone might actually take a look at the code and find the backdoor. But if you have a matrix, how do you know what the backdoor is or how it's encoded? You have no way. There is no tooling to find such backdoors. But more interesting than that is that when we went and talked to our customers and partners and said, okay, you're doing machine learning, you're doing AI at scale, at production, on real-world systems, what do you care about? And they said, well, I don't care about denial of service. I don't care about mispredictions issues. I have a much bigger and more pressing concern. I'm scared that someone is going to steal my IP. And the reason for that is very simple. Because if you're paying a bunch of data scientists very high salaries and they're working on building that model for, let's say, a year, 10 of them, that's 10 man years to build a model, and you paid a couple of tens of millions of dollars to purchase the data, you have now invested over $20, $30 million to build that model. But in the end, what you get is a couple of megabytes in size. So if I can access the system and steal that model, I win. And I took all of your IP and I ran away with it. And that's what scares them the most right now, real production systems. The second thing is they're very, very scared of somebody changing the behavior of that model without anybody knowing. And right now, machine learning models have no control system. They have no control planes to say, OK, somebody changed the model. There is no integrity checks. There's no signatures being applied. We're not there yet. We are 15 years back compared to IT security. So in order to discuss how actually it would look like to build an attack and what are the ramifications of building such attacks, I'm pushing the mic over to Ezra.
So thank you, Guy. I need to start by saying that I am more nervous talking here in Israel than talking everywhere else in the world. So bear with me and be patient. Cool. So to build an attack, we need to understand some stuff. What are the things, what is the background that we need to know, and what are the particular areas that we need to target as attackers? And what do we need to have access to? Because as we know, if you don't have access to anything that is machine learning, you cannot really perform an attack. So let's start. We can go by two different directions. We can either attack the system infrastructure that is empowering the machine learning framework, the machine learning process, or we can attack the math. If you remember, we were talking about what is the entire machine learning process from the moment that it starts with an input that it's being parsed into internal representation, which is system, and then it's being passed to the algorithmic phase, and then it's going to be mapped. The output would be a number that will be mapped to a label, which is going to be, again, a systematic phase. But again, the most important thing that I want to talk here is that if we cannot convert the input into an internal representation, the entire machine learning process doesn't work. And I'm going to say it again. We need to convert the input into a matrix, which in the world that we're familiar with, and whenever we love exploitation, we need to do it with parsers. And parsers are hard. I mean, if we are familiar with vulnerability research, most of the vulnerabilities that we had ever seen are related to converting files from format A to format B or parsing or whatever. Parsing is extremely hard. Oh, and not only that, on top of parsing being hard, the guys that know how to develop machine learning AI are very good at developing machine learning AI. They are not very good at developing file formats or parsers. And sometimes the common solution for these guys is to say, let's bring libbmp to our application. Let's just use an external dependency into our project. So they are bringing an upstream dependency into their stack. And now they are bringing the traditional problem of supply chain and patch management. So imagine that you are bringing into your stack libbmp, and there is a new patch, and this new patch, it's modifying the behavior of how the bitmap is being generated or it's parsed. The model won't be relevant, and there might be extremely bad affecting changes. And not only that, if you are doing image recognition and you only support a single format, your framework doesn't work. I mean, if you are only supporting a very strange format or bitmap or whatever, you need to support multiple formats. So a lot of external dependencies, a lot of external parsers, a lot of external libraries. And this is for whenever you are doing exploit development, this is magic. When we have a lot of formats, the first thing that we want to do is to fuzz them, because who has time to do code review when there is so much code to review? And then we thought, cool, if we're going to fuzz the frameworks, we're going to fuzz the entire machine learning framework. And in this case, what we started working with was Café. But Café has a problem. Whenever you are fuzzing it, you are running the entire machine learning process. You are running the entire matrices multiplication, which is slow. But Café uses a library called Open Computer Vision, which it's still heavy lifting, but it's faster to do the attacks in there. The speed is medium. We could have also gone to library BMP or whatever, and it would be extremely fast. But as you know, they are not using the entire code pad that is available in here. And my favorite one, which could just go upstream, and we don't need even to do fuzzing, just find vulnerabilities in the libraries. And the problem is not now we need to see if it's patching here, it's workable, there is a code pad that arrives there. Bottom line, we choose to fuzz OpenCV, and we found hundreds of crashes. Now, when you have hundreds of crashes, life can be good or bad, depending how is your perspective, but you need to triage them and develop an exploit. And guess what? We did it. Now that we have our crashes, we need to arrive to this kind of attacks that our customers are concerned about. And the question was, if we have remote code execution, could we accomplish any of those scenarios? So let's try to see it in action. The first one was a denial of service, where we tried to abuse a memory leak. On the left side, it's the attacker. On the right side, it's going to show the status of the system. Normal, everything. We go to the library where we have our machine learning application that is actually parsing the input and is going to give us a prediction back. We send it our denial of service. Take a look at the status of the memory here. It's normal. We run it. The memory arrives to full utilization. We have a crash, and it's game over at this point. The input was only 10Ks. We managed to use 7 GB of memory. It was amazing. And the business impact is falling services, downtime costs, but nobody likes denial of service. We came here to see remote code execution. So in this case, we found a crash where we were being able to abuse the heap, a heap exploit. And again, left side, it's going to be attacker. Right side is going to be, we're going to see it in a few. At this moment, we see that the hostname, well, it's being cropped in this screen, but over here is the same hostname called WM. We go again to the same library. We run our exploit. It's a cool story because over here there was auto buffering, and the name of the file it was also part of it. We run it. And at the second one, we are now going to connect to a reverse shell, to a shell that we opened with this heap overflow. We see I did a mistake. Hostname, the same hostname that we were before. And now we have full code execution. We can see all the files that are in there. And remember this is going to be important later. So
just to clarify, the entire attack was an upload of an image that we constructed, and we got a remote code execution on the server, just to make it clear.
So full RC by a single image. The machine learning model, it's completely broken. What can we do with that? RC was not going to go to our goals. So if you remember, we have access to see all the files in the system, and we can also modify, or we can also send some shell code that is going now to modify the label file. So let's take a look at how a label file looks like. A label file includes the number and the description of the specific field that we're going to take a look in now. So number 10 is going to be whatever, and 13 is Jonko, it's Snowbird. Now we run our exploit. Segmentation fault, as expected. We open this file again, and every prediction Now it's going to say hacked. I am not going to do this the next demo because it's trivial. You all know what is the gist of it. If I can steal the model, I managed to do whatever I want. I was able to steal the file system. I can do whatever I want and steal the model. So yeah, RC is our king. However, we don't always have an RC. And you know what we do whenever we don't have an RC? We do something very, very, very smart. We talk to Guy.
OK. So we saw what we can do when we have an RC. But whenever we don't have an RC, there are a couple of different attack methods that we can employ. So one of the most interesting ones, and this is very interesting because all we need, the entire premise of this attack, is that we have some sort of machine learning that has public-facing API that I can access. And in that API, it gives me responses. It's not a very hard assumption to make. So what I would do is that I would use that machine learning system up there as a service, that black box. I will use it as an oracle. And I will build queries, and I'll send queries over to that black box, and I will get responses. And I'll take these sets of inputs and outputs that I've now generated from that system, from that oracle, and I'll train my own system based on those inputs and outputs. So what I can do is actually I'm building a cloned system without any specific knowledge of what happens in that black box somewhere in that machine learning service. But because of the way that machine learning encodes information, behaves, and learns, it means that if somebody else already done all of the hard work, all of the heavy lifting of developing those algorithms, I can just access the system through the public-facing API and clone all of that information out just by asking the right questions. So when we ran these experiments, we were expecting that we're going to see like hundreds and millions of numbers of queries needed in order to do these kinds of cloning. The reality was that we managed to do most of our cloning attempts in under 5,000 queries. So we got some responses, OK, so we'll do API limits. Really? How would that stop an attacker who is determined to get there? He would just pay money and steal the information. We're talking about paying a couple of dollars for 5,000 queries and stealing $30 million worth of a model. So that's not a huge game. Maybe I can block his IP. I can rate limit the IP. Well, that's laughable. So I just use 10 different computers to do these queries. So currently, there are no kind of mitigations against these kinds of attacks. I want to explore this a bit further. There are actually 3 different types of these cloning attacks. The Whitebox attacks is the easiest one. Because you have full information about the construction of the machine learning system, you just need to clone information out by using your queries. And this sounds like that's very strange. Why would I have full access to the machine learning? Somebody is trying to hide that information from me. Well, that's true. But most companies hire data scientists in order to build their machine learning models. And data scientists have theses published in universities, which you can go and look at. They have papers published in conferences. You can go and take a look at that. Sometimes the companies themselves go and publish their algorithms and information in conferences and such. And you can learn a lot from that, too. So there's a lot of publicly available information about what the company is doing and what kind of method it's employing that is very useful for me as an attacker to zoom in and focus my targeted attack. Very helpful. The second type of attack is Greybox. And that means I have no idea what's going on in there. I have some domain knowledge about the topic. An example would be I have a traffic recognition system, so a traffic sign recognition system. So somebody built a system that can identify a stop sign and a speeding sign and a serpentine sign, etc. And he based his learning on the US National Traffic Sign database. Excellent. I have no access to the US one, but I have access to the Brazil one. And the Brazil traffic signs and the US traffic signs share a lot of similarities. So I don't need exact knowledge about what they use to construct their system. I just need the same domain. And if I'm still playing in the same domain, I can still clone the system. And we've done that. Blackbox is much more difficult. Blackbox means I have no idea what the system is doing, and the system is not giving me full information. So I'm asking it questions, and sometimes only feed me back a bit of those results. Maybe the top 2 results, maybe the top 3 results, not the entire set of the results. We are currently experimenting with that. We have some success, but it's much more challenging than the other 2 types. But what if the attacker has access to what you're doing in the training phase, so actually when you're constructing the model? Well, that gets to be a bit scarier. I mentioned backdoors before. Backdoors is scary because in machine learning, you have no way to detect that a backdoor was actually employed, and you have no way to detect what kind of triggers would trigger that system. So I'll give an example. Let's say you have an intrusion detection system that was trained to identify malicious payloads as they flow through the network. So you take a bunch of malicious payloads and tell the network, look, the neural network, look, this is a malicious payload, learn. And you take a couple of benign payloads and say, look, these are benign payloads, learn from that as well. But somebody also introduces a magic packet that whenever you see this magic packet, the system thinks, well, this is a benign payload. I take the system, I bought it off the vendor, and now I'm running my own tests against it. I give it malicious payloads, it works. I give it benign payload, it works. I have no way to know what the trigger would be, what the magic payload, what the magic number would be to trigger the benign behavior for malicious packets. So backdoors can be introduced into machine learning products by whoever designed the system, even without their knowledge, maybe government involvement. And we have no way to know if such a problem existed in that model when we're buying it. We have no way to reverse engineer it. There's another problem, and that is that the number of inputs that are mapped out into an output, it's much larger than you would expect. So you would expect that whenever a system sees a picture of a cat, it would translate into a cat, and that would be a good thing, because that means the system is working. But the reality is, it's not looking at the picture of a cat to determine that that is a cat. It's looking about the relationship between the pixels, color values, histograms, statistics, in order to determine that this is most likely a cat. And that means that there are a lot of other images that might also translate into a cat. And I'm going to show you a couple of examples. So there was a debate for a very long time, can these types of attacks actually work in the real world? Because in the real world, we have 3D objects. We have image, we have our perceptions, we have zoom, we have scale, we have rotation. And people in the community said, the data science community, well, it can't be done. Well, surprise. This is not an actual turtle. This is the 3D printed turtle, just to make sure we haven't harmed anyone. And if you look closely at the top of the shell, you see like red dots. These red dots are interpreted by the machine learning system. In this case, it's Inception v3 by Google, as that turtle being a rifle, if you look on the left-hand column. And that means that if I'll take that sample and put that sticker on something, the machine learning system will now think that this is a rifle. It's not looking for something that's long and elongated with a brown handle and something metallic and tubular in nature. It's looking for specific relationships. And if I can find those relationships, which, spoiler, it's pretty easy to do, you can do whatever you want with the system. So machine learning systems are very good at solving very specific problems, but they break horribly whenever you start playing and messing with them. I want to give you an example about privacy, a very important topic in today's world. Machine learning systems are leaky as hell. And I'll give you a very simple example. Let's say that we have a machine learning that a vendor built to detect diabetes. So he took a couple of people with diabetes and built his data set. And now we have a working prediction model that will tell us if somebody has diabetes or not based on their blood test. So here comes Joe. And Joe is being tested by the system. And it says that his risk of having diabetes is 7.4%. Or maybe Joe has a risk of 35.3%, and then the insurance company can decide, should I sell him a policy or not, based on the risk score by that system. But then Philip comes along. And Philip was part of the original data set that the system was trained on. Because it was part of the original data set, his prediction numbers are going to be much, much higher. So much higher that I can almost certainly say that he has diabetes. I leaked his information out of that machine learning model. And we can do that in a couple of different areas as well. I want to also mention face recognition. So face recognition system is something that we've learned to expect in the last year or two, not just to detect where faces are in images, but also who is that in that image. So here are a pair of glasses. If you put them on, you're now someone completely different. So in this example, this is Mila Jovovich. You can buy a simple pair of glasses and become whoever you want. And this person has become Carson Daly. I've seen another image, another video, which I can't share here, that somebody did this, and he went through the airport, and he was recognized as Vladimir Putin. Not a good idea. So what are our key takeaways? For researchers, This is an interesting area to poke at. A lot of things that you can do. There's stuff to do on the infrastructure side of how you actually deploy the machine learning systems, which currently needs a lot of attention to make these systems more robust, more interesting, and more resilient to attacks. For attackers, wow, this is great. Nobody's touching that. There's lots of stuff to do. If you're coming with an attacker mindset, this is a very interesting field to look after. But more importantly, if you're a defender, if you're here in order to protect your systems or to protect your organization who is deploying those AI models, you should think about how you sanitize your data. You should think about what kind of control system do you have around that data. You should think about the way that you're communicating data. For example, you might think that if you have a TLS connection to bring the data back to your data center, that's fine. Well, that's not fine if somebody compromised the sensor or the data input. TLS doesn't do much. In the end, there's no AI. It's just someone else's code. I want to acknowledge a couple of people who are on our team and did this research. Omer, Adi, Dennis, Reizi, Adel, Sapir, and Oleg. So our thanks to everyone on the team. A couple of references if you want to have some very light reading for dinner. And in the end, we would be happy to discuss this further, to answer questions. Just come and catch us after the talk. Thank you.
And self-promotion at 2:45, I'm going to deliver another talk here.
Any questions? Yes. I heard the first part. The question was is there any history of somebody stealing IP? Yes. Yes. I can't share details, but yeah, that's a big concern and has roots in reality.